Okay, let's continue from where we left. So remark number 2, every vector U of V has a unique negative vector, which we can denote as minus U. So we can prove this. So let's prove. Now suppose V1 and V2 are negative vectors. Suppose so V1 and V2 are negative vectors. Of U. Then means that U plus V1 is equals to 0 vector, and U plus V2 is also equals to 0 vector. So if those are the negative vectors of U, then therefore V1 equals to, so this V1 is the same as V1 plus 0 vector. V1 plus 0 vector. Now, if we replace this 0 vector by this, then it means V1 plus, where there is 0 vector here, we replace by this one, U plus V2. Then this is so like that. So this is actually similar to, so we can bring this V2 to this side, and then we take the V1 here. So it is similar to V1 plus V2 plus plus U. Yeah. So it can commute. So it can commute. So we can bring this here. So V2 plus V1 plus U. And then this can also be written as V2 plus U plus V1, since this one commutes. And therefore, this is the same as V2 plus 0 vector, since U plus V1 is 0 vector. So therefore, this is equals to V2. So it shows that the negative vector is unique. So they're equal. They're equal. Remark number 3, if U plus V is equals to U plus W. If U plus V is equals to U plus W, then, so if this is in a vector space, V, then V is equals to W. Then V is equal to So we can use the cancellation law to see that. So so we can call, which is called the cancellation law. The cancellation law. So how can we prove this? Proof. So we can note that minus u plus u is equals to u plus minus u, which is the same as u plus minus 1 u. And this is equals to 0 vector. And that is equals to 0 vector. Then coming back to this, then minus u plus, if we put this one like this, plus u plus w is the same as minus u plus w. And this is also equals to minus u plus u. Plus w. And this is the same as minus 1 u plus u plus w. And this is equals to 0, since this one is equals to 0 plus w there, which is also the same as w plus 0. And therefore, this is equals to w. So therefore, u therefore 0 plus v is equals to 0 plus w. And this is also the same as v plus 0 is the same as w plus 0. And therefore, v is equals to w. V is equals to w. So it shows the cancellation. Cancellation. Cancel. Okay. Any question up to that? All right, let's look at example number 1. So which kind of, what are the examples for the vector space? And we have actually looked at this. So example number 1. So one of the vector spaces which we looked at is the Rn. And I remember writing the properties of Rn. So one of the examples of vector space is Rn. So Rn is a vector space. And this is a vector space under the vector addition and also the multiplication of a vector of Rn by a scalar. We have actually looked at it, so you can go back to your notes. Another one which we looked at is the matrices. If we have M matrix, which is an M by N matrix, then the sets of all M by N matrices with real entries is a vector space under the matrix addition and multiplication of a matrix by a real scale. And we also wrote the properties. So the two of them satisfies the 8 axioms. So they satisfy the 8 axioms. So you can add, you can subtract, you can multiply by the identity. They can commute. Yeah, so they actually satisfy the 8 axioms for the vector space. Okay, let's look at another theorem here, which is 1.2 theorem. In vector space V, we have 0 U, which is equals to 0 vector. When you multiply a vector by 0, then you get a 0 vector. Also, when you multiply a 0 vector by the scalar, you still get a 0 vector. Also, and minus U is equals to minus 1 for U elements of V and C element of real. So you can multiply vector by 0, you get a 0 vector. You can multiply a scalar by a 0 vector, you still get a 0 vector. And minus U is the same as you can factor out minus 1 and then. Okay, so you can look at your textbook and there are some proofs. We can prove. Another example, example number 2. Example number 2. Let's D be a non-empty subset of R. Let's D be a non-empty subset of R. The set V of all real valued functions on D is a vector space under the addition, whereby if we add the 2 functions there of x, it is the same as f of x plus g of x for all x elements of D, where f and g are elements of V. Also, we can multiply by the scalar multiplication, whereby c by f of x is the same as c of f of x for all x elements of D and C elements of real number and the F element of. So if we have two functions, F and G, then the two functions F and G can be written as F plus G of X. And so you can distribute X. Also, when we multiply by the scalar, then it can be X. So this is basically a vector space because the two of them here will satisfy the A axioms. They will satisfy the A axioms. First of all, you can start by commutativity, so they can commute. F plus G is the same as G plus X, G plus F. The next one you can multiply by the identity, which can still be 1F is equal to F. Also the negative of this F, the negative of the function F is negative F. So negative F multiplied plus F is the same as zero function. Is the same as a zero function. So what you need to do, I will give you a sketch of this. I'll not prove it. It's very long. So because you need to prove the 8 axioms. You need to prove all of them, whether they satisfy 8 of them. So what you need to do first, so the proof, the sketch. So you can still look at your textbook. So you need to check non-emptiness. You need to check whether this is non-empty. So first of all, you start with this. You need to check the non-emptiness. So to check the non-emptiness, then the zero function from let's say D to the real number, the zero function D to real number. So this is the zero function. And this zero function can be written as 0 of x is equals to, so it is from this to this. So 0 of x and x is in D. So 0 of x is equals to 0 for x element of D. Yeah. Since 0 is in V, then the set is non-empty. Since we have this zero function in D, then it is non-empty. Now, after doing this, then you prove the 8 axioms. So you prove all of them. Prove the 8 axioms. So you need to start from commutativity. You come to associativity. So if you have like 3 of the function f, g, and h in V, yeah, then for associativity, then f plus g plus h, all this of x, and this can be this. So you can start from that, and that is equals to, this is basically equals to f. So it's the same as f of g of h plus h of x there. So it's not very hard to do. So you can go check your textbook. Okay, now let's come to the next section, which is the polynomial. What is a polynomial? The polynomial 1.3. So what is a polynomial? So a polynomial, which we can name as P, is of the form P of x, which is equals to an xn plus an minus 1 xn minus 1 plus a2 x squared plus a1 x plus a naught. So the polynomial can be written like that. That is the polynomial. So for example, the quadratic polynomial can be written like this. So if we have p of x equals to, let's say, x squared plus 1, so that is still a polynomial. That is a quadratic equation. So this has the degree of what? Of 2. That's the degree of 2. Another one can be the p of x equals to x cubed plus 3x squared plus maybe x plus 1. That is still a polynomial, and that is a polynomial of degree 3. The highest power of x here is the highest power of x is 3. So p of x equals to a n x squared plus a n minus 1 up to a naught is a polynomial where the scalars a naught, a1 up to an are the coefficients, and x is called indeterminate, and x is called the indeterminate. So a naught, so these are the coefficients. And these coefficients are actually real numbers. So they are real numbers. Now, define the degree of px to be equals to a naught, or let's say we can start from an xn minus 1, sorry, xn. Let's write it again. Px equals to an xn plus an minus 1 xn minus 1 plus a2 x squared plus a1 x plus a naught. So the degree of this, so the degree of p is equals to n if an is not equals to 0. The degree of p is equals to an. So the degree of this polynomial is an is n if an is not equals to 0. So the highest power of this is n. So the degree of that is 3. Now when p is 0 here, then the degree, when p is 0, then the degree there is negative infinity if p is equals to 0. Is equals to 0. Okay. Another thing, two polynomials are equal if they have the same degree and same coefficients for each x raised to k. So two polynomials are equal if they have the same degree, the same coefficients, each x raised to k. Each x raised to k. So you know how to add the polynomials. So you can also add the polynomials, and you can also multiply the polynomials by the scalar. You can add the polynomials, and you can also multiply the polynomials by the scalar. So if we have the polynomial p of x to be equals to a raised to an x n plus a n minus 1 x n minus 1 plus let's say a1x plus a naught and PLQ of x to be equals to let's put this one as BM XM plus BM minus 1 XM minus 1 plus B X plus B naught B1 X plus B naught. The two polynomials there. Then we can add. So you can add the two polynomials. So these polynomials P plus Q of x can be equal to. So this can be equal to. So this can be equal to an xn plus am plus 1 xm plus 1 plus am plus bm xm plus a1 plus b1 x plus a naught plus b naught. So you can add the two polynomials. So you can add this and that. So a, so you can check this a plus this, and then add to the one which is equal to b here, which you can now bring this a and plus b and raised to x and like that. So this happens when m is less or equals to n. When m is less or equals to n. So when m is less than n or equals to n, then so we can write that. Now, when m is greater than m, then we can still write this as bm xm plus bm plus bn plus 1 x n plus 1 plus an plus bn xn plus a1 plus b1 x plus a naught plus b naught, where m is greater than n. This happens, so m is less than n, so this can be greater than n. Now we can also multiply this by a scalar. Now, if we have the scalar c and we multiply by the polynomial cp of x here, then this is the same as you can just multiply by c of an xn minus xn, sorry, plus c of an minus 1 xn minus 1 plus c of, let's say, a1 x plus c of a naught. C of a naught, where c is an element of real. So you can multiply by this. Now let's look at an example. Example number 3. A polynomial is also a vector space. A polynomial is also a vector space. So we can still add the two polynomials, and we can still also multiply by the scalar, which is an example number 3. The sets of all polynomials with real coefficients, which we can write this as the capital P. You can write as capital P is equal to. So that is how we define a set. An xn plus an minus 1 xn minus 1 plus a2 x squared plus a1 x plus a naught, where a naught all the way to an are elements of real number and n is greater or equals to 0 is an integer. So that polynomial, the polynomial of real coefficients, can be written as a set of these, whereby a naughts are elements of real. So this polynomial here is actually a vector space. So is a vector space under addition of polynomials and multiplication of the polynomial by a real coefficient or real scalar, by the real scalar. So it is also a vector space. So it satisfies the A attributes. Satisfies A attributes. Now, the zero polynomial, or we can say the zero vector in P, or in this capital P, is the zero polynomial. The zero vector is the zero polynomial. And this happens when all the coefficients are zeros. This happens when all the coefficients are zeros. All the coefficients are zeros. Also, a negative vector, the negative vector of P of X equals to ANXN plus A1X plus A0 in P is negative P of X, which is equals to negative AN XN plus negative A2 X square plus negative A1 X plus negative A0. That is also at 0. Okay, come to the next section here, which is this number 2, the subspaces of a vector space. The subspaces of a vector space. I think we had done something on the subspace in the previous section. So we said, so let's look at definition 2.1. A subspace of a vector V is a subset W of V, which is a vector space under addition and scalar multiplication on V. So when you take a small portion of V, which you can have as W, then that is a subset. So it's a subset of V. So this subset is also a vector space. So that small portion of V is also a subspace. It satisfies the 8 axioms. So when you take a small part of it, then it is also a vector space. So that satisfies the 8 axioms. 2.2. And this one is a theorem. And this is what we call the subspace test. The subspace test. So how can we test the subspace? So we test this one by use of 2 of the 8 axioms. We use the 2 of the 8 axioms. So if we let V be a vector space, a subset of V, which is W of V, is a subspace if and only if the 0 vector is an element of W, the 0 vector is an element of W, and CU plus DV are also in W for any C and D elements of real number, and U and V are elements of W. So for this to be a subspace, then subspace that it should satisfy the 2. First of all, the 0 vector should be in W, and the addition and vector, the scalar multiplication should also be in. So those are the two ways of testing whether it is a subspace of. So those are the two ways of doing this. Okay, so we can prove this. So we can prove. So how can we prove this? So we need to prove it in two ways. If we let 0w, yeah, the 0w, which is a 0 vector in W, to denote the 0 vector of W, we have 0w to be equals to 0w plus 0w, and 0w equals to 0w plus 0. And all these are vectors. So therefore, 0w plus 0w is equals to 0 vector. Is equals to 0 vector. So this 0 vector is actually in what? So it's in the also, if C and D are elements of real number, and U and V are in W, then CU and also DU or DV are also in W. So they are also in W. Now, if we let U and V to be elements of W, then U plus V are equals to 1 U plus 1 W or 1 V. And all these are in W. So they're actually in W. So it shows that this is a subspace. So it shows it is a subspace. Now, the conditions or the axioms 1 and 3 and 5 and 8 are actually true for W. So we can write the axioms 1 to 3 and 5 to 8 are true for W. So they're actually true. So it follows the 7 axioms there are also true for W. So they're also true for W. So it shows that that W is a vector space, is a vector space. Okay, now let's look at another example, example number 4. Show that W1 and W2 are subspaces of a vector space V, then W equals to W1 plus W2, which is equals to W1 plus W2, where W1 and W2 are elements of W. So show that W1, W2 are subspace. So in this case, you need to use the subspace test. So you need to start from the 0 and then you count addition. So to use the subspace test, then so we can prove this. So we can use the subspace test. So we can say, since W1 and W2 are subspaces of V, then the 0 vector is in W1 and also, and then the 0 vector is equals to the 0 vector plus 0 vector, which is also in W. So since W1 and 0 vector W, therefore 0 vector is equals to 0 plus 0 is in W. Now, if we let U and V to be in W, if we let U and V to be in W, and C and D to be an elements of real number, then we find that U1 and V1 are elements of W1 and U2 V2 are elements of W2. Elements of W2. Then U is equals to U1 plus U2, and V is equals to V1 plus V2. V is equals to V1 plus V2. So then, since CU1 plus DV1 are elements of W1 and CU2 plus DV2 are elements of W2, then CV plus DCU plus DV are equals to CU1 plus VU2 plus DV1 plus V2. And this, we can distribute the constant there, which are equals to CU1 plus CU2 plus DV1 plus DV2. Then we can collect those terms there, and this is equals to CV or CU1 plus DV1 plus CU2 plus DV2, and we realize that these are in W. So those are in W. So therefore, using the subspace test, then it means that this is actually the subspace of the vector. Subspace of the vector. Okay, we can meet on Monday and then